Okay, so the biggest problem I have solved already. Thank you very much for the invitation to give this talk. Maybe I should start with telling you the first time when I met Boris. There he was touring Europe and Germany in the early 1980s. And apparently he had heard about this Petri nets. So he visited Karl Adam Petri in Bonn. And they discussed a little bit, and I was sitting next door to Petri. And then they came over to my office. And Petri said, I should tell this guy a little bit about the, say, technicalities of Petri nets. So I started telling him, but after 5 minutes, he started saying, aha, yeah, now I understand how it works. So the next question should be this and that. And then the next interesting point should be that. And suddenly it was not me who told him something, but he was just developing things by himself. He only asked, how do you call this and how do you call that? So I was really impressed how quickly he got the point and how systematically he put exactly the right questions about invariance and whatever. And from that time on, we met frequently in Germany and in Israel. The last time I remember was I wanted to visit him in Rehovot, and I was standing in front of the house. Of course, I could not ring the right bell because I could not read the names on the bells. So I had to wait until somebody came to read me the right name. Okay, breathing life into predicates, that's a title that is a little bit very immodest because it is in some sense loosely related to a paper that was written by David Terrell and Werner Damm 20 years ago already, where it has been called Breathing Life into Message Sequence Charts. My talk is a little bit related to that, but not too close. And in principle, one principle of my talk is completely different from the talks we have seen so far, because what we have seen so far is about results. And what I will tell you is more about notions and about notions. So let me start with a very classical notion of a specification. In the logical sense, we have a signature. This is an alphabet. It looks like this. So what do we have? We have sorted symbols for sets. We have sorted symbols for constants and functions and for predicates. You know all this. And then you have a lot of structures that belong to the signature. So you replace the symbols, the set symbols by concrete sets, the constant and function symbols by concrete functions, and the predicates by relations. You know this very well, and the specification employs terms over sigma and variables, and they represent sigma structures. That is the standard way to do it. And we have specification languages. I don't name them all here. And my point is now the question how to introduce, sorry, I want to put away your nice pictures, but I can't. Okay, it doesn't matter. So the question is how to include dynamic aspects into this, say, constant word, because a specification is a constant item, and there have been many attempts to introduce, say, dynamics into this. And what is the central idea? You have the notion of a state. The state is part of a sigma structure, or sigma structure itself, and you have a next state function that assigns each state another state. Usually it's in specification languages, it's written in this form, assignment statement, where the left side A is a constant symbol, usually called a variable, but conceptually it is a constant symbol. And on the right side, you have any kind of a term, also including variables. And well, there's one exception of this. So abstract state machine of Yuri Gurevich, there you can have on the left-hand side any term and not only constant symbols and variables. Okay. What is my central point is that the sets, the given sets, and the predicates, they remain. So whatever in this dynamic version of specifications is updated are the function symbols or the constants even only. And well, you have the notion of a run, that is a sequence of states. And also we will talk about the question if a sequence is always a good idea, and you will see it is not. And the predicates are used to describe properties of your systems. And here is where logic comes in. With these predicates, you know all this, you build all the logic around. But that is a standard way to do it. And we suggest something slightly different, but which will have fundamental consequences. Namely, we suggest you update the predicates. And that means the predicates are the things that change, and that change their extensions. And that has a lot of consequences which are very useful, and that I will show to you. I take an example which, of course, you all know. That's the example of the philosophers, dynamic philosophers. So you have 5 philosophers, 5 forks, and two functions, L and R, and each function assigns each philosopher a fork. And you know how they do it, such that neighbored philosophers share a fork. And now the green stuff, you have predicates. There are thinking philosophers, there are eating philosophers, there are available forks, and there are engaged forks. And now to describe, to step from one state to another state, we just describe what changes the predicates. When is a predicate fulfilled and when it's not fulfilled? And the change of predicates is used to describe the behavior. Whereas in the usual case, the change of states is described by help of constants and functions, and the predicates are used to describe just properties of what you have done. Okay, now we want to make together a specification, what is called a decent meal of the philosophers. So what is a decent meal of the philosophers? It's intuitively very clear. The meal is decent if each fork is alternatively used. So you know each fork is used as a left and a right user, and if they alternate the use of the forks, then a meal is decent. And now let's try to develop a decent meal. So we say a local state, and that is a fundamental point. A local state is a predicate and an element. And here the predicate was available forks. For instance, fork 1 is available and fork 2 is available. And the philosopher A is thinking, and then you can say a step has a result that fork 1 is engaged, thinking philosopher is now eating, and the available fork is no longer available but engaged. And then the fork is given back, and we reach the same set of local states again. Okay, here is another such step where philosopher B is thinking and eating and thinking again and using his fork. And you see the philosopher A and philosopher B, they share the available forks. So if we may glue this in this way together, now the forks F1 was first used by philosopher A and then used by philosopher B. Now let's continue a little bit. Here is philosopher E, who shares fork 2 with A, and they also may be glued together. And now you can say, aha, so in one step we don't have just one philosopher eating, but 2 of them may also be eating together. And it is in a lockstep fashion. And indeed, many people think that concurrency is about this sequence of locksteps. So where in one step, not only one event occurs, but many events occur. However, this is far too close, and I will show you what this means. And to this end, I make a shorthand notation. So instead of writing all this, I only write what you see here on the right, the available forks and the philosopher engaged. And even more, we abstract away and say, aha, this is the representation of philosopher A taking his 2 forks and eating and giving his 2 forks back. And now let's have this and continue. Here is philosopher D. He also takes 2 forks and gives 2 of them back. And now we continue. E takes the fork of A and of D and makes his behavior, his run. And here we have philosopher B. And now for the sake of graphical representation, these 2 nodes should be one node. It is the philosopher B who takes this fork and who takes the fork that he shares with A, and he is eating and giving it back. And now we continue. Here is C, and here is A the second time. Here is D the second time. Here is B the second time. And I think intuitively it's very clear how it develops. Each fork is always shared alternatively by its users. So why do I show you this example? I show it to you because here is no longer global states. You can no longer distinguish global states. You cannot even distinguish locksteps because this is just a partially ordered structure, and this is no longer a sequence of steps or of locksteps. So with this tiny notion of local states, you get a structure that is no longer definable in the classical way as a sequence of states and steps, even not when you try to make the steps locksteps. Okay, here's another chaotic meal, but I think I don't go into details. So some of you may know this as the true concurrency semantics. And now we discuss the problem, why is this kind of behavior representation and semantics representation, why that did not really develop? It is until today not standard way to describe behavior. And I think the reason is the following: it's technically not very elegant to cope with this so far. And this partial ordered runs, yes, okay. And now comes the point that I will do. We have with this kind of local states, we can see they form a classical monoid. You can just represent this kind of a situation as a sequence of local states, just as you do it in sequential runs. So if this is a monoid, you will ask, what is the alpha bit of this monoid? And to this end, I introduce again the forks, as you can see them here. And here you see the alphabet. The alphabet is A, B, C, D, E, but each element has each philosopher has also attached his fork. So these are the elements of the alphabet. And now the fundamental question is, how do they compose in this monoid? And I give you an example here. You have D and A, E in this monoid. And if you compose them, this is how they compose. And now you have a word which has on this left side F2, F3, and F4. And on the right side, I'm sorry, I cannot read this because here I have your pictures and I don't know how to. Here I have it. On the right side, you have F2 and F3. And in this simple way, you can compose, you can describe this kind of, say, relatively complicated structure just by writing this sequence of symbols. Okay, that is one of the fundamental points I wanted to show to you. And this, as you remember, was the decent meal, and you can write it this way. It's first A and D, and then B, C, D, E, A, and you continue this in very often. Of course, this is no longer a free structure because the same structure can be written down in general in different ways. Okay, I think I should not use too much time, but we still have some time, I think. I will show you a big example or a glimpse at a big example where we can exploit all this. And the example is, again, we have as a local state a predicate and element. You have seen this already. And here you see a typical local state. There is a shop, an internet shop, and you have ordering customers, and one element is Ute, that is an ordering customer. Here you have another local state. These are the running purchase orders. So this is one of them. Ute is buying or is purchasing 3 elements, 1p1 and 2 times elements p2. Here you have another 3 local states where there is inquiries if these elements are available. And you may ask yourself, but I've written this down so small. But the reason is because now we have a way to write down how to make a step from one local state to the other local state. And we do it with a box like this, where we say, Ute submits a purchase order like this. Well, I think most of you have seen at least a graphical representation of patronets. And in fact, this becomes a patronet. Here you can see the purchase order for 3 elements is now disassembled into 3 local states because each of that is acquired locally by itself. And then you can continue a lot of things. And what I'm showing you here is not a system, but just one behavior, just one partial order. And you can see there's one part of this big partial order is within the customer. Here is a part of the partial order within the order management, and here in the inventory management. And here is the whole single partial order. You see, it starts out in the customer's case. It goes in here, but it comes also back. Then it goes in here and goes back. And then it goes to the freight forwarders and they bring it back to the customers. Still, you must believe me, this is a partial order. And if you would try now to write this down as a classical sequence of states and steps, you would never get this insight that you get here, namely, how is it structured with respect to these 6 components. Okay, how can we represent all this? Well, we just write the composition operator that you have seen already. It also applies here, and you have this sequence of partial components. Each of these colored boxes is a partial order, and if you compose them with this composition operator, then you get what you wanted, namely the big partial order. Okay, this was one behavior. Now, of course, we want to have a system model, but we want to speak about many such partial order, many behaviors. And now we go from local states, which is a predicate to an element, to the notion of a state component. A state component is just a predicate, which can, of course, develop a lot of local states. And here you have a typical component which has predicates. The circles are predicates. The boxes describe the behavior, and they may be inscribed by formulas like here. And on the arcs, you have terms which include variables. I don't want to go into details how this kind of steps have been defined. Many of you may know high-level patronets, and it's roughly in this style. This now is the model of this retailer system. It has 6 components. It reminds you a little bit to the structure of the behavior, and rightly so. And this is already, it looks very graphically, but this is a formal model. You can really formally prove that each order is eventually served. A good is delivered only if it has been ordered before, or each requested reservation is eventually acknowledged. Each mandated article has, so if the order management orders something in the warehouse, then it is guaranteed that it's available, etc. So all the behaviors you need, you want, you can prove in this system. And again, you can write the composition just with this one single composition operator. And now it may be that you are really interested to understand how this operator looks like. So how is the composition defined? And there is one fundamental idea which I will show you here. So you may have seen in the example already that each such a module has an interface which is separated in the elements of the left side and the elements of the right side. And this is fundamental here because what we are doing is the following. we compose a system in the following way. The right side of the left module is composed with the left side of the right module. And here we see purchase order occurs in both sides, so they are composed. But I've written this already here. So they can be composed and they can be composed, but the deliveries cannot be composed. The question is, where do the deliveries go? Well, they go to the right side of the composed system. So now the composed system of A and B has as a left side those two elements, and as a right side it has those three elements plus this one. So this is the fundamental point of this composition operator. As I said, this goes in the composition. I'm almost at the end of my talk. So this whole system is called HERAKLIT, according to a Greek philosopher who says something is always moving. And what do we include into this? It has three components. Firstly, we include task structures or relational structures and signatures. And we start as far as possible as logic does. So we follow logic in the very strict sense. Only where logic starts to talk about properties, there we start to talk about behavior. The second thing is patronates, and from there the fundamental point is that the step affects only a local part of the system. So a step in the class conventional way, a step updates a global state. So if you want to really model a really big system like a company, then it makes no sense to identify global states at a big company, because you never would objectively find global states. And to the second point is no step in a company affects the entire global states. So that is the contribution of patronates. And the third contribution is this composition calculus, where I've shown you how the composition operator works. So all this is based on fundamental theorems. And the most fundamental theorem is this one, that composition is associative. I think implicitly you have in the examples, you have almost seen it or assumed that this is the case, because it would not make sense if it would not be associative. If you try to compose a lot of components and you would have to include always brackets, it makes no real sense. And the second basic theorem is compositionality. So the runs of a composed system is more or less the runs of the composition of the runs of the components. Well, if you compose two runs of a component, the result may be no longer a run, but if you exclude all these non-runs and consider only the runs, then this is a true theorem. So the second question you may have, and I answered this question before, and now you may say, from literature, we know there are so many different composition operators. For every calculus has its own composition operator. So how can it be that for us one composition operator is enough? And the answer is very simple. We suggest to describe everything that you have here in the difficult composition operator, you put it into an own component that we call an adapter. Okay, everything that you describe in the composition operator, we describe in an own composition, it's called an adapter. And then you place the adapter in between A and B, and then you compose A with the adapter and the adapter with B, and that's it. So composition is now completely separated from all the technicalities that many other formalisms put into the composition operator. Okay, that's it. So breathing life into predicates means breathing life into the circles of a patronate, which gives us an infrastructure to model statics, dynamics, and architecture of discrete dynamic systems. I do all this research together with a colleague, Peter Fettke from Saarland University, and you find more on this web page. We are now also engaging companies that use this formalism. I thank you very much.
Thank you, Wolfgang. Any questions, remarks? So I have a question about composition. So this is, you said it is not one operator, it's just a family of operator. Yes, you insert adapter.
It is exactly one operator. But when you want to put something into the composition, for instance, data or anything else, then you should not put it into the operator, but into the adapter in between.
Okay, thank you. Thank you. Any more questions? Remarks? Okay, thank you very much.